Welcome back to another series of one-on-one lecture instruction. So, as always, what I want you to do whenever we go through a slide and there's an image that's pasted there or there is red underlined words, I want you to go ahead and make sure you write them down. What does today look like for us? Well, our main learning objective for today is to compare solids, liquids, and gases in terms of compressibility, structure, shape, and volume. Our demonstration of learning for today is going to be given 6 questions on solids, liquids, and gases. Students will correctly compare the compressibility, structure, shape, and volume 5 out of 6 times. So that means we need 5 out of 6 questions answered correctly for mastery. We're going to begin with shape and volume. Remember, anything that takes up space and volume is considered matter. So we're going to look at these atomic structures and compressibility of each one. We're going to also look at the energy, movement, and spacing between each particles. As you can see, we're going to start with our solid. We have that structure right there for a solid, so you might want to take some time and pause the video if you have to pretty much replicate what you see there. For solids, energy is very low. As you can see, the movement of these particles, since the energy is so low, they're just vibrating in place. So even though solids look like they're not moving at all, the particles are vibrating in place. They do have some sort of energy in there. The spacing is very close together. So for solids, particles are very compact. They're tightly packed together. We're going to move on to liquids. As you can see in the image, the particles are kind of scattered. The energy for liquids is moderate energy, so there is some energy there. The movement of particles allows for sliding past each other. So unlike solids, which are vibrating in place, liquids have particles that are always sliding past each other, moving around. Liquids have particles that are very close together too, but they are not stuck in place. They're not in a fixed position. So they're not as compact as solids. If we look at the last image on the left for gases, you can see that the gas particles are pretty far spaced out, and you can see some vector arrows, which means it's showing the movement. For spacing, these are far apart. You can clearly see that in the image. The energy, they have very high energy. So kinetic energy, the energy for movement is very high. They're always moving around. Usually higher temperatures have higher kinetic energy, which is where you'll find your gases. The movement, it's a random movement in all directions for each particle, and particles move in a straight line. So basically, now we're going to compare the compressibility. Compressibility is how easy it is to press something into a small space. So once again, compressibility is how easy it is to press into a small space. Gases are the most compressible states because they have a lot of space between the particles. So that means when it comes to it, if we wanted to compress them, we can press them until the particles are very close since they're so far apart from each other. There's lots of compressibility possible for gases. Now we have these images for the shape and the volume. Now in this case, the first one is an image of a solid. The solid itself, as you can see, the particles are arranged. They have a specific pattern. They hold their shape. Liquids are kind of scattered. They're still compact. They're still pretty close to each other, but they're not as connected. They don't have a fixed position. That means they're not in just one given area. If we saw movement, which we will see later on, you would see that these particles are touching, but they're also moving past each other. And the last one, gases. Gases have a lot of space in between them. The movement of these items is random, and it has the highest compressibility just because of the distance between particles or how far apart they are. We're going to do a quick check. Now, as far as we know, solids, as we said, the structure, which is the example right there, that's a solid in a container, so a square container. It keeps its shape, it keeps its structure because the particles are tightly packed and held in place. Compressibility, it's not really compressible just because the items are already as packed as they can be. The shape is definite. That means we know what the shape is. It keeps its shape. And as we can see right here, this cube keeps its shape. And the volume is definite. The amount of space that it takes is going to be the exact same amount no matter where you place it. Liquids are a bit different. If you can see in the image, the compressibility for this item, it's barely compressible. That means the particles are very close to each other already, not as tightly packed as solid, which gives some compressibility, but they are very close to one another. The shape, it has an indefinite shape. That means it doesn't have a specific shape. If I pour it into this cube container, it'll take the shape of whatever volume it can hold. If I put it into a triangular one, it would take that shape. If I put it into any container, liquids flow, the particles slide past each other, so it allows them to change shape into whatever container they're put, or at least as much volume as can be fit in there. And they have a definite volume. That means no matter what shape the item will be, if I have, let's just say, a specific volume like 20 milliliters, no matter what shape I shape those 20 milliliters into, or what container I place it into, it'll always just be the definite volume, which in this case would be 20 milliliters. Gases are a bit different, and as I said, this is a different representation down here. They're all in the same container, so in this case, you can see the particles are scattered. They're very far apart from each other. The compressibility for this is very compressible, just because of all the space between them. Its shape, it has an indefinite shape. That means it can take on the shape of any container that you place it in. It does not have a specific shape. If you have a circular container, it'll turn into a circular shape. If you have a triangular one, triangle shape. No matter what shape you put in it, since its shape is indefinite, it expands to fill out the container and take its shape. The volume for gases is not definite either. That means no matter what size the container is, when I put my gas in there, the particles are so far apart they will keep on expanding because of all the extra energy they have, and they will take the shape of what container you put it in. That is an indefinite shape for this container. We're going to do a little summary for this item. It's going to be a brief explanation. We're going to use Fat Colorado simulations to kind of see what it looks like when these particles are actually in motion. So I'm not going to actually write down the summary, I'm going to say the summary based on our observations. So here we go. If we can look at the particle, we're looking at a solid first. The solids in this case, as we can see, they're stuck vibrating in place. So there is movement, there is energy there. The energy is quite low, but it's present. And as you can tell, the shape stays the same. It moves around a bit, but it keeps its definite shape. It has a specific volume it takes up, and they are very compact, so you cannot compress them that much. Let's look at neon in the liquid state. We see in the liquid state, the particles are still compact, but there's more space between them. The particles have more mobility, that means they can move around more. If you follow any specific particle, you can see it doesn't stay in the same place. It can actually slide past other particles. But this is what a liquid looks like at a molecular level. Particles are compact, yet spaced out, and they are not fixed in place. That means they can slide past each other, they can move around. Let's take a look at neon and its gas state. Neon in its gas state, the particles are very, very, very spread apart. That means we can see it take the shape of the container. We can see the movement moving all over the place, and it's random movement. And as we said, gases take the shape of their container. They have an indefinite volume because they can do that. They can expand to fill out the container they need. And that's pretty much it for these items. All we need to do now is use our knowledge to go on to the independent practice. I want you to go on the states of matter independent practice and do your best job. As you work on this, I will be walking around. We will have some discussion in class about this. So thank you so much for your time.